Alright, in this video I'm going to present to you the paper Text2Motion from natural language instructions to feasible plans. And the motivation behind this paper is that they want to make robots understand natural language instructions. So some examples of instructions you can see here in the image. And the background is because there's a lot of work trying to do this, and one of the more famous one is sequential, and there is some limitation with this work. For example, it greedily predicts actions without any foresight. So the natural language model just predicts each action as it goes along. So there's no way to verify if the full plan actually will get you to the correct goal. And this is the overview of their approach. So it consists of three main parts. First, you have the instruction part. So this is the input that goes into the model. So you have a natural language instruction, you have a symbolic state, you have a set of available skills that the robot can perform, and the natural language model is asked to first generate a symbolic goal state. Here you can see in this case it's on blue rack, and then given this goal state it's asked to generate a sequence of skills that should fulfill this goal that it predicts in the first step, and then in the last part it will act on these skills. So there are some prerequisites that we need to understand to grasp this paper. So the first one is that they use a library of skills, which they call LSI, and each of these skills consists of a policy and a parameterized manipulation primitive. That is what takes the action and then performs the motion on the robot. And then each skill has also a language description. And they work in an environment that is a Markov decision process, and maybe you're familiar with this, but a Markov decision process consists of a state space, an action space, a transition model, a binary reward function, and an initial state distribution. So to perform a skill, an action is sampled from the policy that is associated with the skill and then fed into the manipulation primitive. And then if this skill succeeds, a binary reward is given a 1, otherwise 0. And the objective here is to find a plan, which is a sequence of skills that are likely to satisfy the instruction and should also be able to be executed successfully. And this can be described as a joint probability of the skill sequence and the success rate, where the skill sequence depends on the instruction and the initial state, and the success probability depends on these parameters. But as we know, the instruction is not important for the success probability, because any sequence of skills would be successful at a given probability no matter what the instruction was for those skills. And also the skills are dependent on the actions, so they rewrite this probability like this. And then they have this component which they call geometric feasibility planning. And essentially the goal of this component is to say, given a skill sequence, how likely is this to be performed in the environment that the robot is in? And they use some prior work by the same authors, which is called sequencing task agnostic policy, or short STAP, which you can see the formalization of down below. It's not important for our purposes in this video or for understanding this paper to understand this equation, and I won't go into detail on this part, I will have a link to the description of this paper in the comment section below. But this is one approach to perform the geometric feasibility planning. You can use other approaches, but this approach also returns the sequence of states that is predicted given the action sequence. And here are the methods they use in their approach. So they have two different strategies for generating the plan or the skill sequence. The first one is a shooting-based planner, where it asks the LLM to predict the full skill sequence. The other one is a search-based planner, where it does a form of greedy search to evaluate one skill at each time step. But first, they need to know where do we want to go. So what is the goal we're trying to reach? And to get this, they ask the LLM that they ask it to generate a set of symbolic goal states, and it's given the instruction, which is in natural language, a set of objects from the environment, and also a library of predicate classifiers, which you can think of as the potential relationships that could exist. So this is the the domain that we want the goal to be expressed in. And they also have a satisfaction function, which evaluates if a set of goal states are satisfied in a given state. And what this means is that at least one of these goal states is true in the state. And then a sequence of skills is said to satisfy an instruction if there exists a state in the state trajectory produced by this sequence of skills that satisfied any of the predicted goal states. And for the shooting-based planner, they ask the LLM to get the top K skill sequences. Then they use the geometric feasibility planner to give the success probability of each of these sequences. And if these skill sequences meet the goal conditions, they're added to a candidate set. If the set is empty, that means that planning has failed. If it's not empty, they return the top one plan. And for the search-based plan, they do sampling of skills iteratively. And how they do it is they calculate for each skill, they calculate the score. And this score is a combination of the usefulness and the feasibility of the skill. And the usefulness is like, it answers the question, how likely is this skill to help reach the goal? And the feasibility asks in this case, the geometric feasibility planner, how likely is this skill to be successful in the given state? And this is approximated, as you can see here, with Q values for a given policy. And then, so for each iteration, or for each time step, we ask the large language model to generate K candidate skills. And first, the invalid skills are filtered out, and it's done by this equation, which, briefly explained, takes an ensemble of Q values, so you have multiple Q functions, and you check the variance between the different outputs for these Q functions. If they exceed a threshold, then they filter out this skill. And then they return the skill that is has the highest score. So that's why it's called greedy. At each step, it just looks at the best skill given this time step. It doesn't really plan ahead. And the Text2Motion full pipeline, it combines these two strategies. First it checks if the shooting returns a valid plan, then it just returns that one. If it doesn't return a valid plan, then it goes on to do a greedy search, gets the best skill for this state and the goal, and then generates the next state, does shooting again, and then iterates until it finds a plan. And the experimental setup consists of 3 types of tasks. The first one is the long horizon, which requires plans of length 6 or more. The second one is lifted goals, where in the goal specification there's not a single valid goal state, but there could be multiple ones. So for example, here in task 3 you see the task is how would you move 3 of the boxes to the rack, and one potential goal state could be that the blue, yellow, and the red box are on the rack. And for the last task type, they call it partial affordance perception. And what this means is that you cannot determine which skills you should use. You cannot just extract the skills from the instruction. So for example, in task 4 here, how would you put one box on the rack? There's no action that is put. You have actions such as pick and place, where you can see in task 1, these are explicitly stated in the description. And then the evaluation metrics they use are quite simple. They consider a plan correct if it reaches the goal state, and also if the execution of the plan succeeds. And the baselines are sequential, but they add a generator scorer that limits the number of skills before scoring them to increase efficiency. They do the same thing with the inner monologue model, and they use the shooting and greedy search strategies on their own, and then compare this to the full model. And here you can see the results. Maybe no surprise that their model outperforms all the others. You can see here in the first 2 tasks that the Text2Motion performs on par with the shooting, also in the third one. And this is because the shooting returns a valid plan, and then they're essentially the same. But for task 4 to 6, grid search outperforms shooting, and also Text2Motion outperforms even grid search. And here are more fine-grained results. So here you can see what kind of failures or success the different models have. So in the partial affordance perception, we see that shooting performs really bad. It doesn't find any plan. But Text2Motion still performs pretty good. And most of the errors come from the execution errors. And then without partial affordance perception, you see that Text2Motion and shooting performs equally well. Always a plan is found, but sometimes it doesn't execute. So what are some limitations of this paper? One thing they mention is the recency bias, which can create a cycle of repeating skills, which means that you perform the same skills and you end up in the same state multiple times, which you want to avoid. It's not an optimal planning strategy. And also they mention that there are a lot of different components in this approach. So the value functions are trained separately, the dynamics model is also trained separately, and errors in these models can contribute to the overall error. And then some of my own thoughts about this paper is that, well, they do this long horizon planning, which is probably a good thing compared to sequential, which only predicts actions and then act on them instantly. But compared to sequential, they use a symbolic representation of the environment, and somehow you need to get this symbolic representation. I assume they do that manually. They don't talk about it in the paper. So the question is, if you need this symbolic representation, is it actually an improvement on sequential, which can go directly from images, which is more domain independent, you can say. And another limitation, I think, is that they use the language model to predict the goals. They never verify that the goals actually are correct, and then they check if the plan succeeds with the predicted goals. So it could be the case that the predicted goals are incorrect and the plan fulfills the incorrect goals. So the actual instruction is not fulfilled, but the predicted goals are. And this will give an illusion of correctness. So to sum up the paper, they proposed the model Text2Motion, which is a language-based planning frameworks using LLMs, and they try to solve real-world robotic manipulation tasks. Compared to previous work which predicts an action and then performs the action, they create a full-length plan to achieve the goal and then verify that the plan actually achieves the goal before acting on it. They combine two different search strategies. One we can call one-shot planning, shooting, where they generate the full plan in one prompt, and then we have greedy search, where they prompt a skill at each time step. And the results shows that the search-based planning, so the greedy search, works. It helps when the number of possible plans is large, but the number of valid plans is small. And also the combination of the two approaches outperform both parts. That was it for this paper. If you have any thoughts, any comments, please be sure to leave them in the description below. I'm happy to read those, and see you in the next one.